Okay, now let's consider calculating the determinant of this matrix, this 4 by 4 matrix. And if you know the definition of the determinant, you can just apply that definition to this. So in this case, let's pick this row, the first row. So pick the first element, so negative 1 to the power of 1 plus 1 times this 1 times the remaining matrix here. So that will be negative 1, 2, 4, 2, 3, 5, 0, 3, 7, plus negative 1, this one. So that will be 1 plus 2, and the element is 1. And then the remaining matrix, that is this part. So that will be 2, 1, 3, 2, 3, 3, 4, 5, 7. And the next one is this one. So 1 plus 3, and the element is 1, and the remaining matrix is this one. So that's 2, 1, 3, negative 1, 2, 0, 4, 5, 7. And the last one would be 1 plus 4 times 3 times, and the remaining matrix, let's change the color, that will be this one. So 2, 1, 3, negative 1, 2, 0, 2, 3, 3. And then we calculate the determinants of these matrices. So we need to calculate 4 3 by 3 matrices, determinants of 3 by 3 matrices. And we can go on like this until we get the final number. By the way, the result is just 0 actually, if you do the calculation. But this is very tedious and error prone, so you should wonder if there is any easier way to calculate this one. So how can we make our lives easier? To explain that, let's put this matrix as this, the set of row vectors. Okay, so A4 means 1, 1, 1, 3, and A2 means the second row, and A3 means the third row, A4 means the fourth row. Okay, then there are a few nice theorems that you can use. Okay, first one is that this is actually equal to this. A1, A2, A3 minus A1, A4. Okay, why? Why are they equal? So there is this theorem. So if you have the sum of two matrices, let's say A3 plus B and A4. So let's say the third row, it can be any rows, but let's pick the third row. If this is the sum of two vectors, then we can split the determinant. Okay, this is one theorem about the determinants. So A1, A2, B, A4. Okay, B is another vector. And furthermore, if there are rows that are exactly identical, let's say if we have two A1s, okay, so the first row and the third row, they are the same rows, okay, they contain the same numbers. If the two rows are the same, then the determinant is 0. Okay, so combining these two, actually there is another one. And if you have, let's say, A1, A2, A3, A4, if you have some constant multiplied to one of the row vectors, you have just constant times this determinant. Okay, so this constant can be taken out. if there is one constant in one of the rows. Okay, so by combining these three things, we can show that this is actually equal to the original determinant. 3 minus a1, a4. So first of all, we can split this into two determinants, a1, a2, a3, a4, plus a1, a2, negative 1 times a1, a4. And we can put this negative 1 out. 2, a3, a4 minus a1, a2, a1, a4. Now we have these two rows in common, so this part should be equal to 0. Therefore, this matrix is actually equal to the original matrix determinant. Okay. So if we subtract the first row from the third row, what we have is 1, 1, 1, 3. The second row is the same. And so 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. 5 minus 3 is 2. And the fourth row stays the same. Okay, and we do a similar thing. So let's subtract the 2 times the first row from the second row. Okay, then that will give us, so 2 minus 2 times 1 is 0. So first 1, 1, 1, 3, that will be 0. And negative 1 minus 2, so 2 times 1 is negative 3. And 2 minus 2 times 1 is 0. And 4 minus 2 times 3 is negative 2. Okay. And let's do the same thing with the fourth row. So we subtract 3 times the first row from the fourth row. So 3 minus 3 times 1 is 0. And 0 minus 3 times 1 is negative 3. And 3 minus 3 times 1 is 0. And 7 minus 3 times 3 is negative 2. So now look at this matrix. We have actually the same rows here and here, from which we can immediately conclude that this matrix should be, determinant should be 0. So that's a lot easier than the original method of applying the definition of the determinants. So if you do this, you have to calculate a lot of determinants, and you may make some mistakes along the way. But this one is a lot easier. So in this case, we got the same rows. So we happen to have this, but if we didn't, still, this is easier to calculate because these values are all 0. So if you apply the original definition of the matrix determinant, it is just negative 1 to the power of 1 plus 1 times 1 times the rest of the determinants. So that's this. 1, 2, 2. And the rest is 0 because instead of taking the rows, we can pick the next one. So that will be some 2 plus 1 times 0 times some determinant plus negative 1, 2 plus 2, wait a minute, 3 plus 1 times 0 and some determinant. Right, so this and this matrix, and this times this matrix, this times this matrix. So everything else will be 0 except for the first one. But the first one is indeed actually 0 if you continue to compute this determinant. So in any case, just make everything 0 except for one of the rows. Then it's a lot easier. Okay. Next, let's try a little bit different example. Actually, this matrix is almost the same as the previous one, except for this element. Okay, previously this was 3, but now it's 4. But anyway, we can still apply the same method. So this should be equal to, so let's subtract 2 times the first row from the second row. So the first row remains the same, and the second row becomes 0. And negative 3, and 0, and negative 2. And subtract the first row from the third row, we get 0, 1, 2, 2. And subtract the 3 times the first row from the fourth row, we get 0, and negative 3. And now we have 4 minus 3, that's 1. And 7 minus 3 times 3 is negative 2. Okay, now we expand this matrix based on the first column. So we get, I just skip the details. We get 1 times this matrix. Okay, as I have explained before, everything else would be 0, so we can just ignore them. Negative 3, 0, negative 2, 1, 2, 2, and 3, 1, negative 2. Now, we can apply the same method, but we can use another simplifying method. So let's say we have, okay, let's write this as A1, this as A2, and this as A3. So this is like A1, A2, A3. And if we swap any rows or columns, actually, let's swap these 2 rows, then we have negative A2, A1, A3. So for any determinants, if we swap 2 rows, then we get negative of the original determinant. Okay. So if we do that, we get, so we swap the first and the second rows, we get 1, 2, 2, negative 3, 0, negative 2, and negative 3, 1, negative 2. Okay, and negative sign here. Okay. Okay, now let's swap again the first column and the second column. Okay, then we have, again we have another negative sign, so negative 1 times negative 1 is positive. So we have 2, 0, 1. So this column comes first, and the next comes 1, negative 3, negative 3, and 2, negative 2, negative 2. Okay. And let's see. Let's make it, okay, let's subtract 2 times the third row from the first row. What do you get? So this one will be 0, and 2 times negative 3 is negative 6, so 1 minus negative 6 is 7, and 2 minus 2 times negative 2 is negative 4, positive 6, so we have 0, negative 3, 2, 1, 3, negative 2. And let's swap the first and the third rows. Then we have 1, negative 3, negative 2, 0, negative 3, negative 2, and 0, 7, 6. Again, look at this. We have all 0 here, and 1 times these things, this matrix. So the result would be negative 1 times this determinant. And that's easy to calculate. So negative this times this, so negative 3 times 6 minus negative 2 times 7. So that will be, let's see, that's positive 14. That's negative 4 times negative, so that should be positive 4. So this is the result. So again, just applying the definition is not a good idea because it's just too tedious to calculate. So before calculating any determinant, think about simplifying it first. And that will make your life easier.